Welcome to this brief summary of a series of projects taking place funded by BEIS as part of the Offshore Marine Strategic Environmental Assessment Programme. This is collaborative work, and we've been looking at the underwater UXO clearance operations, and particularly processes called high order and low order. So why is understanding UXO clearance operations important? Well, it turns out that many of our historic sites for both dumping and mining, you see here in the blue, are World War II mining sites, and red are actually World War I, and also post-war dumping of ordnance in our oceans has significant overlap with marine energy sites, for example, offshore wind, as we can see from here. And the number of controlled clearance operations has gone up significantly in the last few years. And typically the way this is done is you would take a modern piece of explosive, 5 or 10 kilos of plastic explosion, you see here in the demolition pack, that will be placed next to the historic charge, which might be much bigger, up to maybe 400 or 500 kilograms, and you would explode that. It would detonate. A detonate is a rapid combustion process. The detonation of the charge would cause a detonation in the thing, and we call that a high order process.
Countdown.
6, 5, 4, 3, 2, 1. There's magnificence.
Oh.
What you saw in the previous video was an example of a high order detonation videoed from about 1.5 kilometers away, and this was a detonation that took place in the Baltic of around sort of 30-40 kilos of historic explosives. So this was a World War II piece of ordnance that was high order detonated with that, and you can see a significant amount of energy associated with that event, and we were able to record that in trials that took place in 2023. But we've also been working collaboratively with a number of major wind farm projects, Moray East and NNG offshore wind, and looking at quite a large data set of high order clearances that have taken place in the last couple of years. These events are loud, they have a significant amount of energy, they can cause seabed damage, and we can look at acoustic signatures, you can see on this figure here, out to quite significant ranges, in this case about 55 kilometres. So, are there any alternatives to high order detonation, which is the traditional practice that's gone on for many decades? And it turns out that the EOD community have been using a process called deflagration. This is described as a low order deflagration. And what this is a rapid combustion, but not at supersonic speeds, the reaction you get with a detonation, but subsonic speeds. And it's a burning process. And this is achieved in this particular case by using a small shaped charge. It injects a plasma-like material into the bulk explosive. That initiates a burning process, not a detonation. And that's a lot less energetic. And so we were interested in looking at understanding what that might mean in terms of the acoustics output. So we were involved in trials in 2019 in a quarry to measure the difference between high ordered clearance detonations and low order deflagration burning processes. So what you're going to see in the next two videos are trials that took place in 2019 in the quarry of firstly a high order surrogate shell. This is containing modern plastic explosive, 5 kilograms of modern plastic explosive, high ordered. And then the second video is going to show you an exact equivalent shell using a deflagration, 25-gram deflagration charge.
3, 2, 1.
As you can see from the video, there was significantly less energy associated with the deflagration versus the hard order, bearing in mind that they were both looking at exact same disposal of the same size charge size. We can see that on this graph here. If we look at charge size versus the peak pressure measured in the quarry, for removal of a 10 kilogram charge size, we could get rid of a 5 or a 10 kilogram things. We're around about a 20 dB reduction in the noise level. You're just using 25 grams here. So the deflagration charge it still has an acoustic signature, but it's significantly smaller than the thing. And that graph extends upwards as well. In the phase 4 work, we were working with charges and doing high ordered deflagration charges and high ordered charges on weapons up to about 300 or 400 kilos. And the net difference between the high order and low order becomes even more significant. In 2022, we were able to do direct comparison trials with real UXO, historic World War II UXO, with the Danish Navy and Aarhus University here in the Baltic. The red dots here are the targets, and the blue dots are an array of hydrophones that we set up over 20 kilometres away in typically around 15 metres of water. Here we can see an example of one of the low order clearance events. This is actually Lemur. This was a 430 gram Mark 6 weapon, and here you can see the before. Top picture shows the before clearance and the post clearance using a low order methodology. And you can see on the right the acoustic signatures going out to about 22 kilometres. The lower plot actually shows the equivalent acoustic signature for a high order event of a similar sort of size out to about 18 kilometres. You can see the difference between the two. During the Danish trials, we were actually able to record 4 high order events, various sizes ranging from a few tens of kilograms up to 300 or 400 kilograms, and 4 low order events of similar weapons in the same area up to about 430 kilograms as well. The square dots on here actually show the high order events, and the circular dots here show the low order events out to ranges of about 20 kilometres. And again, it's very similar to what we saw in the quarry. We're seeing around about a 20 dB difference associated with these. Again, the high order potentially dominated by most of the donor charge in the case of these examples, but with the potential to be much, much higher. So, in conclusion, high order clearance operations for EOD operations are very loud. They have significant acoustic signatures over wildlife, and they can cause significant seabed. If anyone is interested in more information on any aspects of this project, feel free to contact me or any of our partners.
Good afternoon. My name is Nienke Van Geel, and on behalf of my co-authors, I'm presenting some of the results of the Fortune project, which aims to characterize the underwater noise of 2 types of floating offshore wind turbines currently operational in the UK. While the operational noise of fixed offshore wind turbines has been described, the cumulative noise levels from turbine arrays assessed, systematic measurements of underwater noise generated by floating offshore wind turbines are currently lacking. The lack of such empirical data impedes noise impact assessments and is increasingly being discussed as a potential consenting issue. To address this knowledge gap, the Fortune project, funded by Supergen, aims to characterize the underwater noise outputs of currently operational UK floating offshore wind turbines of 2 different designs and their associated infrastructure. Using received noise levels at the monitoring locations, the project aims to back-calculate source levels. Additionally, the project aims to investigate noise outputs in relation to operational conditions, like RPM, and environmental conditions such as wind and current speed. Finally, the Fortune project aims to model the noise footprints of the currently operating UK turbine arrays. Acoustic data were collected for several weeks at 2 floating offshore wind farms on the east coast of Scotland. One is the Hywind Scotland site of Peterhead, run by Equinor, which consists of 5 6-megawatt turbines deployed on spar-buoy platforms. The second site is the Kirkcaldy wind farm of Aberdeen, which consists of 5 9.5 megawatt turbines deployed on semi-submersible platforms and is owned by Grupo Cobra. Data were collected at a sampling rate of 96 kHz and with a duty cycle of 15 minutes per hour. Processing included calculations of 1/3 octave band noise levels on a 1-second resolution, which were subsequently aggregated by wind speed. 2 turbine-related noise sources were identified. The first is noise associated with the operation of the turbines, such as from the generator and rotating blades. This noise is more prominent at low frequencies. The second noise is mooring-related noise, which is typically seen as infrequent broadband noise of short duration, as exemplified by the vertical lines in the figure on the right. This figure presents a roughly 2-minute time period on the horizontal axis and the various frequencies on the vertical axis. The sound intensity is represented by the color bar. To focus on the operational noise only, the impulsive mooring-related noise was filtered out of the datasets, as demonstrated for the same 2-minute period in the bottom figure. To obtain source levels for the frequencies from 25 Hz to 20 kHz, Site-specific propagation models were developed and single turbine source levels under a range of wind speed scenarios were calculated from the measured operational noise. Finally, based on the obtained source levels, the acoustic footprints of the 5 turbine arrays were modeled, here by applying different wind speed as well as frequency weighting as described by Southall et al. For the relevant marine mammal groups present of eastern Scotland. At Hywind Scotland, data were collected during the summer period. Here, the top plot represents the measured noise levels for the 1/5 octave frequency bands from 0 to 48 kHz across the monitoring period at 600 meters from the turbine, with the intensity of sound for each time frequency combination indicated by the color bar. Turbine operational noise is particularly visible at 25 and 80 Hz. The bottom plot shows the noise levels for each of the frequency bands across all 1 second data points, as well as percentile statistics indicative of the distribution of these data. The turbine noise at 25 and 80 Hz is also clearly visible here. At Kincardine, where data were collected during the winter months, operational noise was predominantly present at frequency roughly below 200 Hz, but in contrast to Hywind Scotland, not at 25 Hz. Additionally, mooring noise, visible as the vertical stripe in the top plots, was present throughout the frequency range at both sides. This figure presents the correlation between wind speed and the various 1/5 octave frequency bands. A positive linear relationship was present between wind speed and the frequency bands above approximately 1.5 kHz, and in particular with those of 10 kHz and higher. Additionally, noise levels in the 25 Hz band, and to a lesser extent also the 80 Hz band, increased with increasing wind speed. The right figure shows the measured noise levels across the different frequency bands in relation to 4 wind speed categories. The thick blue line presents the median, and 90% of all data falls between the dotted lines. As already indicated in the left plot, the noise levels at 25 and 80 Hz increase with increasing wind speed. At the highest frequencies, noise level increase and the variability in these decreases with wind speed. The Kincardine correlation result revealed an overall high positive correlation between many of the 1/5 octave bands over 100 Hz. The relationship between noise level and wind speed revealed a negative correlation with the 40 Hz 3rd octave band and a relatively high positive correlation with frequencies up to about 200 Hz, resulting from shifts in the fundamental frequencies and associated harmonics of operational noise with increasing wind speed. Weaker positive correlations were present with the higher frequencies typically associated with mooring-related noise. The current figure represents the source levels across the various frequencies as calculated for single turbines at both floating offshore wind farms. Note that the source levels are for continuous operational noise related to rotational machinery in the turbines, while noise of a transient nature, such as those related to mooring systems, are excluded. In general, the source levels for Hywind Scotland are greater than those for Kincardine under similar wind speed conditions. Interestingly, at Hywind Scotland, the source levels computed for the highest wind speed class were lower than in conditions with lower wind speeds for all but the highest frequencies. Array-size noise fields were modeled for a range of different scenarios. In general, the combined noise of the multiple operational turbines, hereby excluding the mooring-associated noise, is louder at Hywind Scotland than at Kincardine, as exemplified here by the unweighted, close-range acoustic footprint at 9 meter water depth for Hywind on the left and Kincardine on the right. In conclusion, the results presented here indicate that the sound generated by the Hywind Scotland and Kincardine floating offshore wind farms are highly variable both within and between site, with differences in the frequency, duration and intensity of both operational noise as well as mooring-related noise. Obviously, these changes in the structure of signals may be relevant when assessing potential impacts on marine species. They revealed that operational noise levels are related to wind speed with the strongest correlation with the lower frequencies. Additionally, sound intensity of operational turbines was higher for the Sparbor design at Hywind Scotland than for the semi-submersible systems at Kincardine. Both designs produce substantial mooring noise, with noise output spanning the entire frequency range monitored in the current study. Additionally, and in contrast to the operational noise, mooring-related noise at Kincardine appeared louder than at High Wind Scotland. And finally, results from fixed wind, with their fixed seabed foundation and lack of the existence of flexible mooring system and mid-water connector cables, cannot be extrapolated to floating offshore wind when considering noise impacts. The report detailing this work will be submitted to Supergen imminently. With this, we would especially like to thank Supergen for funding this project and our collaborators at Equinor and Grupo Cobra for their support and site access. We also thank Moray First Marine for the help in deploying and retrieving the acoustic moorings, as well as the project steering group members.
Hello, my name is Lucie Herve, and I will present the work I've done during my master thesis 1.5 years ago about environmental impact assessment of electromagnetic fields from offshore renewables on marine species. So I've done this work in collaboration with NatureScot and Marine Scotland Science, but also with the University of Strathclyde. The main motivation of this work was to consider that there's an increasing installed capacity of offshore wind in the UK, and therefore increasing number of cables in the sea, with some uncertainty in the level of risk of electromagnetic fields emitted by these cables to marine species. So there was a need for good practice guidance and recommendations to assess electromagnetic fields' impact in environmental impact assessment. So the method I've used is the following. I've started with an analysis of the available literature and of environmental impact assessment reports of wind farm projects. And then I've conducted interviews and workshops with different stakeholders of the field. I'll comment on it a bit later. So firstly, about current knowledge base about electromagnetic fields effects. I've done a literature review about the research that exists about electromagnetic field effects. What I've seen is that there were at that time a growing interest about electromagnetic field effects with many species-specific studies, and they demonstrated some behavioral and physiological responses of marine species to electromagnetic fields. But there were still a lot of knowledge gaps remaining, such as the impact at the population level, but also effect threshold for marine species. I've also studied electromagnetic field impact in environmental impact assessment reports and how it is considered, especially for wind farm projects in Scotland. In all the EIA reports that I've studied, EMF impact is considered as negligible, but this conclusion is mostly based on the lack of evidence of an impact more than on an evidence that there's no impact. So globally, electromagnetic field impact assessment is based on a lot of uncertainty and many knowledge gaps. So there's a need to bring the research forward. The question is how, and that's why I've done some discussions with different stakeholders of the fields. Also, I've conducted interviews with different stakeholders. What is important to see in the breakdown of interviews, is that there are many different stakeholders interviewed. I've interviewed developers, cable manufacturers, fisher representatives too, but also advisors, researchers, regulators, and environmental consultants. The goal of the interviews was to get in contact with these different stakeholders and identify their viewpoints and potential needs for improvement and guidance about EMF. And then we've organized a workshop with the same stakeholders and some others to collectively discuss ways of improvement. So the main results I've got are some recommendations about EIA for EMF effects. Firstly, the first recommendation that I've done was that uncertainty should be more highlighted in EIA reports concerning EMF effects, because all stakeholders that I've interviewed admitted that there were some uncertainty, but it's not always stated in EIA reports. About mitigation options, what I've recommended was that one type of cable cannot be advised as better than another to mitigate against electromagnetic fields, because we don't have enough evidence that lower electromagnetic field levels are better for marine species. About monitoring, the main results that I've got was that there was a lack of in-situ experiments and electromagnetic field measurements, but there's not enough evidence of an impact to justify monitoring by developer, and developers didn't want at that time to conduct monitoring with this base of evidence. So the recommendation that I've done was to make a collaborative and strategic project to improve the knowledge base about electromagnetic field impacts. This strategic project could be a work of collaboration between different expertises, biologists and electrical engineers, and it enabled to reduce uncertainty and to bring everyone's expertise in a positive collaboration and proactive collaboration. And a coordinated project could reduce the uncertainty, because what I've identified is that there was a common objective of reducing the uncertainty about electromagnetic field impact. So to summarize, this project helped documenting the uncertainty of electromagnetic field impact in environmental impact assessment reports. And also the workshop that we've organized with the stakeholders, as far as we know, was the first time different stakeholders of the field gathered to discuss the impact of electromagnetic field. So this work can be used by the partners as a starting point of a collaborative project based on the recommendations that I've done. Thank you for listening.
Hi, good afternoon. I'm talking today about a series of workshops that my co-authors and I have been involved with. The workshops are focused on bringing greater consensus to the understanding of electromagnetic fields associated with subsea power cables. EMF is a key topic of interest when considering the potential environmental impacts associated with power generation and transmission. We've been working in this novel topic area for over the past 2 decades. However, research has been a bit irregular because the topic kept getting shelved due to patchy and variable knowledge. However, at present there's a lot of interest. This is primarily fed by ongoing stakeholder concerns, regulators recently raising the priority of EMF, and developers being keen to address it, particularly for floating offshore wind. In addition to further evidence required, we identified a need for better knowledge exchange and consistency in approaches to understanding EMFs and their interaction with receptor species. We therefore organised and delivered 3 interrelated workshops, 2 funded through MASTS and a 3rd funded by the Crown Estate OWEC programme. The first 2 workshops are part of a project titled Collaboratively Advancing Our Understanding of Electromagnetic Fields from Subsea Power Cables. The project aim was to undertake facilitated academic engagement with policy and decision makers and also industry to enable strategic research and collaboration to advance understanding of the effects and impacts of EMF. The engagement was through 2 virtual workshops. First, to identify the needs of policy and decision makers, held in June 2022, and the second to identify the needs of industry, held in August 2022. Each workshop's goal was to identify key evidence requirements regarding the potential impacts of EMF. They were an opportunity to identify and address communication gaps and strategically plan to address knowledge gaps in relation to offshore wind cabling and electricity interconnectors. In parallel, a visualization exercise has been producing illustrations to communicate the EMF topic, as it's really difficult to grasp. A final webinar accompanied by a short report will communicate the topic and map out a path towards addressing evidence needs. Both of the knowledge exchange workshops were well attended and received. The key knowledge need for both workshops was to understand the significance of the effects leading to impacts in relation to the consenting and EIA process. To get to this understanding, the participants' comments are shown. High on the agenda was the consenting need for both fixed and floating offshore wind. There's also consistency in modelling and measuring, which included defining the required model parameters and variables to measure. Greater realism in determining the EMF environment and greater realism of the studies used to support them was also important. Development of a standard EMF sensor and a clearer understanding of the range of EMF and the EMF sensitive species, including their different life stages. Cumulative effects and also the engagement with industry were deemed really important inclusions. These knowledge requirements are important in moving along the route to address the question of EMF impact. We propose a route map to address the so what question of is there an impact, defined by the green box here. Essentially, we need to understand if the effect results in population impact that can enable EMF to be retired as a risk, or define the population impact to enable the EMF to be mitigated. This requires the key components shown of the EMF emission from the cable, the encounter rate by the receptors, and their likelihood of response to the cable EMF, and if the impact is deemed significant enough to then consider mitigation. For the first component of EMF emissions, we developed another workshop to draw together the expertise of different disciplines to provide scientifically robust and agreed ways forward for enhancing the knowledge base. The third workshop focused on the knowledge requirement of consistency and realism in modelling and measuring EMF. The workshop was held in person over 2 intensive days of discussion during January at the Royal Institution in London. We had a really great, unique group of electrical engineers and modellers, physical oceanographers and geophysicists, including geomagnetic field specialists, and our biological expertise. The workshop was funded by the Crown Estate OWC programme. The workshop aim was to provide an agreed and standardised approach for estimating subsea cable EMFs in the environment through facilitated expert agreement. The objectives were to agree fundamental aspects for calculating and modelling EMF in both 2D and 3D, associated with high voltage DC and high voltage AC cables. Then to determine how to account for the cable EMF interaction with the local geomagnetic field, followed by consideration of how best to account for motionally induced fields associated with seawater movement. And then finally put the outputs from 1 and 2 into the biological context with regard to the EMF that may be encountered by a receptor species. With 4 sessions within the workshop. Session 1 focused on the EMF, that's the electric and magnetic fields, coming from the cable and the effects of different cable materials and the properties. Session 2 brought in the fact that the cables are not the only influence on the EMF, there's also the natural environment such as the geomagnetic field, and also motionally induced fields, example being tidal water movement. Session 3 was a great discussion on bringing together the data and modelling from the different disciplines that were gathered in the room. And Session 4 focused on formulating the outputs from the previous sessions and looking at them in terms of the biological and ecological relevance. The key outputs from the workshop were that there are minimum requirements to model and measure the EMF, and these can support the licensing process. There's a need for further R&D to provide better certainty when assessing the effects and impacts of EMF on species. The approach needs to be set in the context of current knowledge and evidence needs for supporting environmental policy and planning, and this will also ID the key knowledge gaps and recommendations to improve the agreed approach further. In the coming months, we'll have post-workshop outputs as shown. We'll also look to apply and test the agreed approach within the Flowers OWC project, which will also bring in the encounter rate receptors with the EMF. This series of knowledge exchange and transfer activity has been essential in bringing together what is a relatively disparate and patchily understood topic. We've proposed a route map to address the so what question and have begun addressing the key components here shown in the blue arrowed boxes. The combination of knowing the needs of stakeholders and drawing together different expertise to provide agreed ways forward for enhancing the knowledge base is absolutely crucial to ensure the science evidence base is robust, policy relevant and targeted towards a common understanding. The key message from our workshops is that we need to take account of the different perspectives and understanding of the stakeholders in terms of what the cable is emitting and the use of models to estimate it and also the measurement of the EMF. Whilst also at the same time we have to ensure that we take the perspective of the receptor animal we're considering to ensure that our environmental assessments reflect the reality that the animal finds itself within. We thank the MASTER and OWET programmes for supporting these initiatives and thank you very much for listening.
Thank you.